This lecture is on the law of conservation of energy. It's called "And Whatever Will Be, Will Be." And there is nothing constant in this world but inconsistency, and that's a famous quote by Jonathan Swift. So, what we want to look at is we want to kind of take everything that we've learned so far and we want to combine it into the term called mechanical energy, and then also apply the law of conservation of energy to a system. There are two equations that are here, and the first one is mechanical energy that we were talking about, and the second one is the law of conservation of energy. So we want to be able to use both formulas in this particular case. Now, this is where the majority of the questions come from. So we've taken a look at all the different types of energy, and we've said, okay, work equals changing kinetic energy. Work equals changing our gravitational potential energy. Work equals elastic energy. Well, if work equals all those things, well, then you can set them equal to each other, and we have the law of conservation of energy. So let's take a look at the first one. It says the total energy. A ball thrown up in the air can have both gravitational potential and kinetic energy. So when you throw it off the ground, it's still moving, therefore it has kinetic energy, and it's still some height above the ground, so it has gravitational potential energy. So whenever you have two of those there, how do we know what the total energy of the system is? So we have to kind of come up with a new term for total energy. And that new term we have is called mechanical energy. It is the sum of the potential and the kinetic energy. Now remember, potential energy could be potential energy due to gravity, or it could be potential energy due to elastic. So it's one of those two terms. It could, in fact, be both. So you have to be able to do this to find what the mechanical energy is. Now, mechanical energy is synonymous with the total energy of a system. Um, in most cases, it doesn't account for things like thermal or electrical potential energy. It's mainly dealing with what we call classical physics or kinematics and dynamics. So if you look at this, it's the sum of the kinetic energy and the potential energy. They're all measured in joules, so when we add them together, you're just going to be adding and subtracting at this point. They are all calculated. They're all calculated in different ways, which we've gone over, and they all have different definitions, but they're all energies. So, let's take a look at some of these examples, with the first one being a 2 kilogram spring is compressed and tied such that the spring stores 100 joules of energy. This spring is thrown into the air and is shown to be moving at 10 meters per second when it's 8 meters above the surface of the earth. What is the mechanical energy of the spring? So what I'm trying to solve for is the mechanical energy. Okay. Now, it looks like there's kind of a lot of different energies involved here. So we look at our equation. Remember, mechanical energy is equal to kinetic energy plus potential energy. It looks like there's actually two potentials here. You have the energy due to the spring, and then you have the energy due to the position. But also you have the energy of movement. So it looks like we have almost all of our energies here. So we can go ahead and start and take a look at it. And we can say, okay, can I figure out what the kinetic energy is? Can I figure out what the gravitational potential energy is? And can I figure out what the elastic potential energy is? Well, it turns out the elastic potential energy is easy because it actually tells you that. So you know that's 100 joules. The kinetic energy, you're going to have to use the equation 1 half mv squared, which we've covered before. You know that the spring has a mass of 2, so you have 1 half of 2, and then the velocity squared. Velocity is 10. We square it. 1 half of 2 cancels out, and so the kinetic energy ends up having a value of 100 joules. We also need to be able to calculate the gravitational potential energy, which is mgh. Now, the mass is still 2, gravity is always 9.8 on Earth, and the height it tells us in this case is 8. So when you multiply 2 times 9.8, or excuse me, 2 times 9.8 times 8, what you end up with is 156.8 joules. So now if we want to figure out what the total energy is, we need to be able to combine all of these individual energies together. So we have 100 joules, 100 joules, and 156.8 joules. So the total energy of the system, or the mechanical energy of the system, is 356.8 joules. In the next example, it says you have a 10 kilogram box that has a total of 500 joules. So its mechanical energy is 500 joules. it is stored 4 meters above the surface of the Earth. And it says, how fast is the box moving at this particular point? So I know what I'm trying to do is I'm trying to solve for velocity, which is associated with kinetic energy. Okay, we have this right here. We have the mechanical energy is equal to the potential energy plus the kinetic energy. There is no sort of elastic energy here. There's nothing that indicates it's bouncing or stretching or anything like that. So we can neglect elastic energy for now. So really what we've got is gravitational potential energy and kinetic energy. Or in our case, it would be 500 joules equals mass times gravity times height plus 1/2 mass velocity squared. We have a mass value of 10 kilograms. We have our total potential energy, our mechanical energy, is 500 joules. We also have the height above the surface of the Earth is 4 meters. We do know that it is Earth, so because of that we know gravity is 9.8. So we can go ahead and plug in our numbers now, and we'll get something along the lines of 500 equals 10 times 9.8 times 4 plus 1/2 of 10 v squared. So the first thing that we need to do is we need to solve for this term right here. 10 times 9.8 times 4, and that gives us a value of, when we subtract 500 from 10, or excuse me, when we subtract 500 minus 10 times 9.8 times 4, we end up with a value of 108. So we have 108 equals 1/2 of 10 v squared. Now, 1/2 of 10 is 5, so when I divide both sides by 5, I end up with a value of, that I can go ahead and take the square root of, and you end up with a value of v equals 8.85 meters per second. Okay, this is a lot easier. It seems like it's more difficult, but basically this is the same thing you would do as if you did kinematics to solve for one particular thing and then canceled everything out. It just makes it a lot cleaner. It's all in one particular equation. So if we look at the next example says, what is the mechanical energy of the system given the experimental data below? So what you see here is you have a set of data that has elastic potential, kinetic energy, and gravitational potential. Realize that mechanical energy is the sum of all of these. So you would take 25, 10, and it looks like 4. You would add those together, and you would get a value of 39 joules. Because mechanical energy is the sum of both the kinetic and the potential energies of a system.